Learning Outcomes 10.5 and 10.6. Determine the z-transform of a discrete time signal, both functional and series, and find the ROC for time domain functions using tables and integral. We're going to work through this learning outcome with a series of examples. We'll start with this one. X of n is 3 times 1/4 to the n u of n minus 2 times minus 1/2 to the n u of n. We want to determine what is the z-transform and the corresponding ROC for this time function. We can break this into two pieces, an x1 and an x2. If we look in table 10.2, we can see that both of these are transform number 5, which the first one gives us this result because our alpha is 1/4, and the x2 gives us this result because our alpha is minus 1/2. And the ROCs are the absolute value of z greater than the absolute value of alpha. So we know that xn is a combination of the x1 and x2. So our x of z will be the combination of the transforms of x1 and x2. What's a little bit new here is that not only do we need to have both functions, we also need to have both ROCs. And if we look at this, absolute value z being greater than 1/4 and it being greater than 1/2 means that it must be greater than 1/2. Now let's look at that ROC graphically. Make sure you see what's going on here. Z is a complex number in our real imaginary plane. And the absolute value of z is the magnitude of z, and the magnitude is the distance from the origin. We reference everything based on the unit circle, which has a magnitude of 1. Absolute value of z equals 1. So when we're talking about the absolute value of z, or magnitude of z, being greater than 1/4, we're talking about this region, where we're bigger than 1/4 away from the origin of our complex plane. And magnitude of z being greater than 1/2 is this region. So where both of them hold is the area outside of 1/2. Another example. X of n is 3 times 1/4 to the n u of n minus 2 times minus 1/2 to the n u of minus n minus 1. This is very similar to what we had in example 1, but now instead of an n, we have a u of minus n minus 1. So in order to find the z-transform and the corresponding ROC, we again look at both pieces. x1 is the same as in example 1, but x2 is a little bit different. This minus sign goes away, and our ROC is negative because we're now, instead of using transform number 5, we're using transform number 6. Look in your table. Again, the transform of our total function is going to be the sum of the transform of the two individuals. So we add the two pieces, and then now we need to combine the two ROCs, and the combination of being greater than 1/4 and less than 1/2 will mean that we're between 1/4 and 1/2. Let's look at this ROC graphically. Greater than 1/4, again, is talking about being a distance of 1/4 away from the origin. All of our ROCs for the z-transform have a round boundary, whereas for the Laplace transform, they all had vertical line boundaries. And the other condition is that the magnitude of z has to be less than 1/2, so we're inside of that circle. Where both of those hold is a region between 1/4 and 1/2. One more example. This is a series. X of n is delta of n minus 2 delta of n minus 1 plus 4 delta of n minus 2. What is the z-transform and the corresponding ROC for this function? This is what it looks like. Discrete signal, 0 everywhere except for the value of 1, n is 0, value of minus 2, n is 1, value 4 when n is 2, 0 everywhere else. If we look at our table 10.2, property 1 and property 4, property 1 corresponds to delta of n, and property 4 corresponds to the second two terms. So we wind up with this transform. I want you also to look at the definition of the z transform, which says x of z is the sum of x of n times z to the minus n. Well, our x of n are these terms at those n values, an n of 0, 1, and 2. 0, 1, and 2. So we're going to have each of those values multiplied by the z to the appropriate n. Our x of z is x of 0, z to the 0, that's our 1. X of 1, z to the minus 1, that's here. X of 2, z to the minus 2, that's here. Usually we have an infinite series which approximates a function, and therefore we can write it as a ratio of polynomials. But when we have a discrete list, we can go directly from the z transform.